Gate 2019 Thermodynamics. Equilibrium between the carbon and also the graphite which is being used. So the activity reaches in such a state that the total activity of carbon becomes 1. The variation of standard free energies of two oxides is given as AO and BO with respect to temperature. As shown below, the current reference is given as. So, below a certain temperature, the downward are more stable than the oxides are more stable and they are more reducing. They can reduce the oxides which are present on the topmost part. And also, you can take in an Ellingham diagram gas the only line which is in downward direction is CO gas. So you can compare it with it. Also, you can also say through other means also the entropy is negative for an Ellingham diagram. Here, so the slope is the slope is negative and the entropy is positive. So it says that the product has more entropy than the oxides. So it is only possible for gases. So BO is a gas. And if you'll see the other options also, A will reduce BO above temperature T1. No, above temperature T1, B will reduce AO. And below temperature TO, AO will reduce, A will reduce BO. So both options are wrong. The equilibrium temperature for the following reaction at 300 Kelvin is carbon graphite plus 2H2 gives rise to methane gas. At 300 Kelvin, delta H naught is equal to minus 74,900. Delta H naught is minus 80 joule per mole per Kelvin. R is given as 3. Okay. So to find out equilibrium constant, at equilibrium, delta G is equal to 0. Delta G equal to delta G naught plus RT ln K. So delta G naught equal to minus RT ln K. So now you need to find the equilibrium constant at temperature 300. So K is equal to exponential minus delta G naught by RT equal to exponential. The delta G naught value is given as delta G naught can be written as delta H naught minus T delta S. So minus of minus 74,900 minus 300 into minus 80 divided by 8.314 into 300. Okay. So this comes out to be, if you calculate, 7.3 into 10 power 8. Now, the partial pressure of zinc in equilibrium with liquid lead containing 0.03 mole percentage of zinc at 900 Kelvin is. The vapor pressure of pure zinc is given as 900 Kelvin, 0.027, and Henry law coefficient is given as, okay, gamma naught. We know, according to Raoult's law, activity is P zinc by P naught zinc. Not according to Raoult's law, activity is equal to, and this is equal to activity coefficient into mole fraction. And here X is 0.03 by 100. So it is 0.3 into 10 power minus 3. And again, we need to find P zinc. So P zinc is equal to P naught zinc is 0.027. We can write atmosphere in terms of torrs. So 0.27 torrs is by 1.316 into 10 power minus 3 torrs into gamma naught is given as 8.55 into a mole fraction is given as 0.3 into 10 power minus 3. This and this gets cancelled. So you get the P zinc as 0.0526 torr. It is 0.05. Now, the equilibrium concentration of dissolved nitrogen round off to 3 decimal places in liquid iron exposed to atmospheric air at 1873 is Seward's law is followed, where log Kn is equal to minus 518 by T minus 1.063. It's given. Henry's law will follow this one. According to Seward's law, we know weight percentage of N is equal to K into some Seward's constant Kn into root over P and 2. Okay, we know N gives rise to half N2 and K is equal to P N2 for 1 by 2 by weight percentage of N. So from this you get Seward's law. And now Kn can be given as log Kn equal to minus 518 by 1873 minus 1.063. So here to calculate K is equal to 0.0457. So weight percentage N is equal to 0.0457 into, here it is given as atmospheric air. The atmospheric air contains 79% nitrogen and 21% oxygen nearly. So you can take the pressure, partial pressure as 0.79, as total pressure is given as 1 atmosphere. So you can write it in terms of and 0.79 power 1 by 2. This comes to 0.04. Thank you.